So, in this video, we will compare the advantages of the continuous variable quantum computing paradigm, also called as CVQC, to the discrete variable quantum computing paradigm and the classical computing paradigm. So, the first thing that we will compare is the computational space that is available. So, when I refer to computational space, I will refer to the set of all possible states which can be encoded with n basic units of information of that particular computing paradigm. So the basic unit of information in the classical computing paradigm are bits. The basic unit of information in the this DVQC is qubits, and in CVQC it is QU modes. So let's say I have two bits available to us. So at a particular time, I can encode only two possible states with it. This and this. So let's say the computational space available to us with two bits is 2. Now let us move on to the discrete variable case. If I have two qubits available to me, I can represent four possible states with it: alpha 00 plus beta 01 plus gamma 10 plus delta 11. Four possible states I can represent simultaneously. Here, in the classical case, I was able to represent two possible states simultaneously. In the discrete variable case, I can represent four possible states simultaneously with two qubits. So let's say the computational space here now is equal to 4. In the QU mode case, if I have, let's say, two photons, they can be arranged in four modes, then I have 10 possible states can be represented by using this kind of a decomposition. So let me write down all the possible cases. It will be C00, or let's C00. Wait a minute. It will be 200 alpha 1 2000 plus alpha 2 0200 plus alpha 3 0020 plus alpha 4 0002 plus alpha 5 1100 plus alpha 6 1010 plus alpha 7 1001 plus alpha 8 0110 plus alpha 9 0101 plus alpha 10 0011. So these are all the possible states with two photons and four modes available to me in the continuous variable scenario. So we can see that this is how the computational space scales up. In general, we can say that the computational space, it scales up like this. So if I have n bits, then there are n possible states which I can represent simultaneously or encode simultaneously with n bits. If I have n qubits, then I can encode 2 raised to n possible states simultaneously. And if I have n photons in the CVQC case with m equal to 4 modes, or sorry, if I have n photons and m modes in the CVQC case, then I can represent n plus m minus 1 factorial divided by n factorial into n plus m minus 1 minus n factorial possible states simultaneously. So this is how it scales up. So if I plot the comparison of the computing space, then let's say on the y-axis, I have the computing space available to me in the powers of 10, and the x-axis, it represents the n bits, or sorry, n basic units of information on the x-axis for the various paradigms. Then we can see those plots, they look like this, where these red dots, it represents n bits, these blue dots, it represents n qubits, and these green dots, it represents n photons in m equal to 2 into n modes. So the modes, they scale up as the number of particles or the photons increase. So I have plotted them. So for example, let's say I have 10 bits, then this is the computational space or the possible states that will I will have at simultaneously. That will be 10. If I have 10 qubits, then I can represent 2 raised to 10 possible states simultaneously. And if I have 10 photons in m equal to 20 modes, then I can represent 2 into 10 raised to 7 possible states simultaneously. So we say that the computational space available to us, it scales up drastically if we use the continuous variable quantum computing paradigm. So this is one of the advantages of it. Now that we saw that there is a computational advantage to work with continuous variable quantum computing systems rather than the discrete variable ones in terms of the computational space, let us look at how the the advantages from the physical architecture point of view. So this particular photo over here is of the discrete variable quantum computing system, and currently these discrete variable quantum computing is done using superconductors. So we have a superconducting qubit chip which is used for discrete variable quantum computing. Now the issue is that to run these DVQC physical architectures, we need to keep these qubits at a very, very low temperature. If you see over here, the temperature which is needed for this particular chip to function efficiently is around 20 millikelvin. So we need a lot of cryogenics and other kind of uh, setups to run these devices. But now let us see on this left hand side. This is the chip X8, which is developed by Xanadu, and it does the continuous variable quantum computing uh, tasks. Now, if you look at this particular, I think this is the architecture, physical architecture, you will see that there is no cryogenics involved in functioning these systems. So, currently, with the available hardware to us, it seems that in terms of the ambient temperature and pressure needed for the devices to work, the CVQC has an upper hand. Now, of course, there are efforts for creating the room temperature superconductors, but until now, whatever claims have been made have been falsified over the years about the room temperature superconductors. But however, if we are able to achieve these, then we may have these discrete variable quantum computing physical architectures also to be on the same level as the continuous variable ones. But until now, the continuous variable one has a physical advantage also. Now, the next advantage is with the interface. So, quantum key distribution is a cryptographic paradigm where we use the laws of quantum mechanics for the distribution of keys for cryptographic tasks. Usually, these key distribution is done using photons and light-based systems. So, this continuous variable quantum computing paradigm is usually done with the photons, the there is a seamless integration of this continuous variable quantum computing architecture with the quantum communication technologies available. So this is another advantage of using the continuous variable quantum computing paradigm. Now the next advantage is that these systems are efficient in representing certain types of data. So continuous variable quantum computing, it uses continuous variables such as amplitudes and phase of quantum harmonic oscillators to represent information. Now this can allow for more efficient representation of a certain type of data or certain types of quantum systems which are continuous in nature. So continuous variable quantum computing has an advantage in those simulations of those type of systems. Now, there could be many other advantages of using continuous variable quantum computing, and there could be some disadvantages too. I don't intend to list everything in this particular video, but I think whatever is listed till now is motivation enough for the beginner or the person who doesn't know about continuous variable quantum computing to start learning about this computing paradigm.